So we'll look at an example here of a series that we're going to use absolute convergence. We want to show that this series right here is going to converge for all values of x. So it doesn't matter what I put in here for x. I know this series here is going to converge, and I want to show why. Do we know that the terms here, depending on what I put on x, do I know these terms have to be positive? Why? So it's possible to put in a number like 3 pi over 2 in for x here, and we get a negative number here. Now this exponent could take care of that. If the exponent is even, then it doesn't matter if this is odd or even, or I'm sorry, positive or negative. Even if it's negative, the even exponent's going to make it positive, right? But if let's say we have 3 pi over 2 in here for x, and n is 1. Well, then we get negative 1 over 1, right? And we get a negative term here. So to use the test that we've looked at so far, we need these terms to all be positive. So what we're going to look at, instead of this right here, we're going to consider this. We're going to consider the series, the absolute series, that looks the same except it's the absolute value. We do this because we don't want negative terms here. If we can show that the series converges even if all of the terms are positive, if we add up a bunch of positive numbers, infinitely many positive numbers, and they add up to a finite amount, they converge to a sum, a finite sum, then we know that this series here has to converge. So if we look at the absolute series, then we don't have to worry about whether these terms here are positive or negative. Now, with them all being positive, we can use a direct comparison test. You guys remember the direct comparison test? What series could we compare this to? What series could we compare this to that we know if it converges or not? So let's see if e to the x is actually going to be useful to us. So e to the x is, the series for e to the x is going to be what? 1 plus x plus and I'll just throw a general term in here, x to the n over n factorial, and so on, right? So if I know that this converges for any x value, so if I put any number in for x, and I know it's going to converge, then if I can show this series right here is smaller than this series, then I know this one's also going to converge, right? So is there a way for me to show that this series right here is either smaller or maybe even equal to, so less than or equal to this this series term by term? The key here is that the sign of x, and remember we have an absolute value, right? So this absolute value helps us out a little bit, just simplifies things a little bit. But the sign of x is always going to be less than 1, right? Do you guys agree with that? Or I could even say the absolute value of the sign of x is always going to be less than or equal to 1, right? You guys agree with that? Well, that means that the sign of x, or the absolute value of the sign of the x to the nth power, is always going to be less than or equal to 1 to the nth power. What is 1 to the nth power? That's just 1. Okay, even if n approaches infinity, that would be an indeterminate form, 1 to the infinity, but it's exactly 1. Remember when we had the indeterminate form 1 to the infinity, we had the indeterminate form because this right here, this 1 was actually approaching 1. It wasn't exactly equal to 1. So if this is exactly 1 and we raise it to the infinite power, it's still 1. Because it's exactly 1. It's just 1 times 1 times 1 times 1. Infinitely many times, that's just going to be 1. So if I continue with this here, with what I'm doing here, I'm almost where I want to be with this. The only thing I have to do to change this is what? How do I change this into that? Divide by n factorial. So I know that the absolute value of the sine of x to the nth power over n factorial is less than or equal to 1 over n factorial. Now, this means the same thing as this because of the absolute values. The n factorial is always going to be positive because n is going to be positive, or at least non-negative. So the absolute values could extend to the whole thing here. So we know that this series here is always less than this series here. Is this the e to the x series, though? If we came down here and put 1 in for x, e to the first is going to be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus all the way up to 1 over n factorial. And that's what we have here, right? So if I need to rewrite this a little bit to be correct about the way I write it, but this means that the sum of the absolute series sine of x to the n over n factorial is going to be less than or equal to the sum of 1 over n factorial, and that's going from 0 to infinity on both of them. And I know that this series right here converges to e to the first power. I know it converges to e. So since the absolute series here is term by term less than or equal to the e to the first series here, then what do I know about this series? It converges. Why? So we're gonna write out our reasoning here. This is important that we're able to explain why things are true. So we say therefore this series, and I'm actually going to write it without the absolute values, but I'm going to use a term here that means that it works with the absolute values. So this series right here converges what? What? Absolutely. So it converges absolutely by the, what did we use to show that it converges absolutely? What test is this right here? The direct comparison test, because we directly compared it to the convergent series for E. So the problem here didn't ask us to show that it converges absolutely, it asked us to show that it converges. So we're just going to say, therefore, this series converges. I'm not even going to write the sigma.